Okay, class, let's continue our discussion on the locus. So this is the example we started on Tuesday, that we have the fifth order system, which is 1, 0, and -3, and 5 poles at the origin 0, -5, -6, and a pair of complex conjugates is -1 plus minus j. And we have already sketched part of this locus. We figure out so the sections on the real axis, we know from the origin to the 0, -3 is one complete branch, and the two branches um, between these two open loop poles, -5, -6, actually have this merge and break away, and eventually the breakaway branches will approach the asymptotes. And since the order difference is 4, fifth order over 1 first order, we calculate the asymptote angle to be 45 degrees plus minus 135 degrees plus minus. And the centroids can also be calculated by sum up all the open loop poles, which is -13, and the open loop 0, which is -3, and then find the difference divided by the order difference 4, so which is -2.5 is right here, and we found the two asymptotes. Now the only question we need to answer is, now we have two other branches that are supposed to start from the two complex poles, and they should eventually go towards the asymptotes. But the question is, how do they actually depart from this particular angle? Does it go strictly up, or first flatten up, or does it go down first and then eventually go up? So that's the question we're trying to answer. And if we answer that question, how does it go from this pole or pair of poles, these are what we call the departure angle. And last time we have started the discussion, I find out the departure angle can be calculated like this. And let me just start from here and reorganize the terms. And this will be departure angle from -1 plus j should be equal to, so this is negative sign, so I move to the left hand side and move this 180 degrees to the left hand side. And that will give me the angle of 2 plus j minus, and then I still have this -1 plus j plus 4 plus j plus angle of 5 plus j plus the angle of 2j and minus 180 degrees. So minus 180 degrees. So I move that 100 degrees to the left hand side. So this is what we have. And now of course you can do all the calculations you want, and here I'm going to use the math functionality of OneNote to do all the calculations. So this should be what? I'll type it in. The angle of 2 plus j should be a arc tangent of 0.5, so 1 divided by 2 is 0.5, and then minus, okay, and a bunch of them. First should be this -1 plus j. -1 plus j, you should visualize it as actually in the second quadrant. If in the second quadrant, then if I still want to do the a tangent -1, so this will actually give me minus 45 degrees, and if I want to adjust it to the second quadrant, I should plus 100 degrees to this, and you have done this exercise many times. And then can keep minus a tangent of 0.25, which is 4 plus j, minus a tangent, and then 1 over 5, so 0.2, and then minus a tangent 90 degrees. Sorry, not 90 degrees. I'm going to call just minus 90 degrees, and then that's the angle of 2j, and then minus 180. Okay, and if I want to do calculation, do a equal sign and then space, and then you have what? You have 430.8 degrees. So I want to go back and select this part. I'll move this up a little bit. So minus 45 more, sorry, minus 403.8 degrees. Now it's the same if I plus 380 degrees, right? It doesn't really change. And this will be minus 43.8 degrees. And minus 48 degrees is actually something like this. Right? This is minus 43.8 degrees. And this will be the direction. Will be the departure angle, and this is how the root locus will go from the pole. So if I go up to the root locus I have here, I find out that the departure angle should be negative 43 degrees. So if I draw this, this should go this way first, and eventually will go towards the asymptote. So if I zoom in, we'll be able to see. Right, this is what we have. Now, we know the root locus have to be symmetric, so the departure angle of the other one should be symmetric, so it also have to go up in this way, and eventually goes towards the asymptotes down there for the other branch. It has to be symmetric. And this we complete the root locus sketch for this particular system, and we utilize multiple things, right? The asymptotes, the segments on the real axis, the branches. The breakaway angle here is, basically 90 degrees, since 180 degrees divided by the two poles involved. All the branches goes towards the asymptotes. And what we have in this particular example, as we have already seen, that this departure angle should be equal to negative 43 degrees. And it's pretty straightforward. Now, if I want to, let's say, justify this, answer using the actual root locus, I can use MATLAB to do the calculation. And if you want to use MATLAB calculation, let me just start MATLAB, and which will take a minute. But meanwhile, let's again look at this particular system. This particular system says what? This particular system said, again, at a certain point, the system will eventually cross over the j omega axis, right? So when you're going to calculate the gain k that eventually lead the closed loop system to unstable region, again, you can apply the Rouse-Hurwitz criteria, and you will be able to calculate everything that's involved. Okay, so now I have been started. That will give it a few seconds. Okay. But these are everything you need to be able to calculate in terms of the root locus. In this part, the calculated departure angle is important. Meaning you will see this in the exam, final exam apparently, and the quiz. Okay, you have one more quiz, which will be given after the Thanksgiving break. Okay. So, and you should be able to do all of those. Let's see if I have. So no. So if it's not opening fast enough, we'll probably take a break, and we'll look at the MATLAB demonstration in the next video.